So today we're going to be talking about the linear regression, and first we're going to be importing our data, and we're going to be defining the size of the house as our independent variable and the price of the house as our dependent variable. Then we're going to be normalizing it by using the equation for the z-scores. So like that, all our x values would be scaled into the range of the z-scores. And then we're going to be creating some initial parameters, which we're going to be changing these two right here later on to see how they affect the errors. And then we have our cost function, which actually had an error because it had 2 times n in the original, so we eliminated that. And this right here would be the same as our y hat right here. And since we are just, up to here. Since this is being squared, the order in which they're assigned doesn't really matter because the squared is going to make the result positive, so it doesn't really matter which order they're in. Here we have it in opposing orders, but it doesn't really matter. And then over here we have our gradient descent function, which again uses our cost function. So what this is basically doing is that it is going through the this dm equation. This dm equation is the partial derivative of the sum of squares, the mean sum of squares, but with regards to the slope of the linear regression. So what that basically means is that as long as we are changing the value for our slope, these will be giving us the slope of the mean squared error. So by moving through that, we are trying to find the minimum value for our errors. We're trying to find the place where our errors are minimized. And the same thing happens for the y-intercept, but that is being used for theta 0. Another important thing to consider in this function is that x and y are both pandas series in the way that we're using them. So this prediction and these errors are both being both vector calculations. So these are whole arrays, and that's why we're able to use MP-sum right here. And then based on that, we can give our new parameters to our cost function and use it to calculate the mean sum of errors, and that will be appended into our cost history. So this is going to be telling us how much our model is making mistakes by. And finally, we're going to be returning all of the cost history, the final parameter for theta 0 and the final parameter for theta 1, and the vector of our last predictions. And this I added it to show you something later on. So here we can see the final values calculated, and here we create a function using lambda in which we are going to be making a prediction with our parameters, and then we're going to be scaling down our values for the incoming input, so they will also be in terms of z-score, and that will be able to give us a prediction for our price. And here we can see that it takes 1,000 iterations to reach a value close to 0, but when we graph the scatter plot, we see that they have very different values. The model is really underestimating the value of the prices of the house. So what we can do there is that we can change our initial parameters. So since over here we were using the slope, if we change the learning rate to a higher number, this would mean we will be moving across our slope faster. So let's do that first. So if we change this to 0, 1, and then run it again, we're going to see that it minimizes way faster, and also that the values are very close to it. Now, if we say, oh well, the amount of we reach the minimum a lot faster, then it shouldn't matter if we decrease the iterations. And I also thought that at the beginning, but after running the code, I noticed that did not exactly happen. Even though we do reach the minimum faster, we can see that we're also underestimating the values as we did previously. So if we change these to, let's say, 400, then we're going to be having a better result, as you can see here.